So, hello and good morning, guys. Today we will be jumping into discussions around radiation heat transfer. This lecture is just kind of a little bit deeper dive on radiation. It comes off a little more sciencey than some of the more engineering stuff that we cover, but I think it's kind of interesting, a little bit different. And it's a good way to, I think, to end the semester than just saying, okay, here's the alphabet soup that is boiling and condensation heat transfer. We won't go too far into radiation heat transfer because the more you go into it, the more lost you get in trigonometry. And so I think hopefully this gives you kind of just enough to get an idea of what radiation heat transfer is all about without us getting too lost and deep into it. I don't want us to have any issues, those kind of inception issues. All right, so kicking it over to the notes. So do you guys remember how we were able to calculate the heat transfer rate by radiation? Just to see if you guys kind of have that vague memory. Let's see.
Wasn't the formula like sigma A epsilon T to the fourth?
Yeah, that was part of it. There was a sigma, there was the surface area, and the driving force was a Ts to the fourth minus T infinity to the fourth. You're correct in that regard. The missing value is our sigma.
I said
right?
that.
Did you see sigma? I heard epsilon.
I said sigma A epsilon, I think.
Oh, okay. My apologies, Holly. All right, epsilon is our emissivity, right, which is the measure of our abilities, our object's ability to emit radiation. For the maximum is 1, which refers to a black body, which is why we have discussions over black body radiation. Sigma was our Stefan Boltzmanns constant. Thank you, phone, for letting me know that we have class. Where sigma is equal to 5.67 times 10 to the minus 8th watts per meter squared, Kelvin to the fourth. A sub s is our surface area, T sub s is our surface temperature, and T infinity is ambient, or where we're radiating to, essentially. And so if we take a look at radiation in a little more in depth, if I have a hot object and I put it in a box, it's a circular box, I don't know, UPS does weird things. And then I evacuate that air such that everything around that object that has some sort of temperature, let's say it's hot, this T sub s, T1, and around it is a vacuum. Do we expect to have conduction, convection, and or radiation?
Only radiation.
Only radiation. And so what we find is, as Blake stated, radiation heat transfer does not require a transfer medium, but conduction and convection does. You can't conduct something if you're not in contact, and if you're not in contact, it's not going to happen. And by convection, you can't have flow if you don't have molecules to induce to essentially flow. But radiation doesn't care. Radiation can exist and emit whether or not there's a transfer medium involved or not. Further, radiation is the fastest form of heat transfer. And what we find is radiation can occur between two objects separated by a cold transfer medium. What I mean by this is if we're looking at, let's say, the example I always bring up is camping. If I'm, out in the woods late at night, roasting marshmallows. So let me get my stick. Got stick, marshmallow. And I got a fire going. What we find is that we can have radiation heat transfer in both directions, from your fire to the person to the fire, irregardless of the transfer medium as well as the temperature of the transfer medium. Which is why when you're out in the woods and it's cold, standing by a fire gets you nice and warm. And so when we start looking at the nature of radiation heat transfer, we really can't, escape the discussion of how it exists as well. And by how it exists, I mean, the discussion and exploration of electromagnetic waves and electromagnetic radiation in general. And so if we're going to look and investigate the thermal energy transfer or heat transfer by radiation, it's going to require so let me rewrite this sentence. So an investigation of heat transfer requires discussion of electromagnetic radiation in general. And so this all started, or our understanding of what we know as radiation heat transfer started, by a man known as James Clerk Maxwell in 1864. So Maxwell postulated that changes in electromagnetic force fields resulted in the emission of what we call electromagnetic radiation, or just radiation for short. Right? So these changes in these energy fields resulted in the emission of energy. And so he created this, theory, published it 1864. It wasn't until 1887 where it was first demonstrated by Mr. Heinrich Hertz. So he basically developed an experiment to demonstrate and prove Maxwell correct. And from this, we learned that the radiation that can be emitted follows a law that states the speed of emission is equal to the wavelength of radiation emission times the frequency in which the radiation is emitted, where C is C naught over N. And C naught is our speed of light, 3 times 10 to the 8th meters per second, and N is our index of refraction. Our vacuum, the index is 1. Our atmosphere, when you're an engineer, it's 1. And if you go through a different medium, it becomes greater than 1. And so at this point, late 19th century, we realized that, okay, we have this energy emission that exists, and we call it radiation, and now we can understand the influence of the frequency and wavelength of the radiation that's being emitted. Then, around 1900, Max Planck developed what we know as quantum theory. Which stated, well, we know about this emission, but what can we say about the energy associated with this emission, right? And so Max Planck theorized and demonstrated over the next, several decades that the energy associated with radiation emission is quantized, and we can calculate the energy emitted in radiation, or E, as H times the frequency, or HC over lambda, where H is equal to 6.6256 times 10 to the minus 34th joules, which is referred to as Planck's constant. All these late 19th century, early 20th century scientists trying to get their names in constants. All right, so now we have an idea of, okay, based on the emission, we know there's energy associated with this emission, and the energy is quantized, and we can estimate the energy associated with that. However, when it comes to our explorations, we're more interested in the thermal implications as well in terms of heat and heat transfer. And so when we consider the implications on thermal radiation, we consider how this led to some of the equations that we know today. And what we found that was developed by, Stefan and Boltzmann, was associated with the energy emission of black bodies. And what they found was that the energy emission of a black body was a strong function of temperature and temperature alone, such that we could correlate the energy emission of a black body at a known temperature as a sigma value times the object's absolute temperature to the 4th power, where we know sigma as the Stefan Boltzmanns constant. And this gave, and we can calculate the energy emission of any object at a known temperature was equal to the epsilon times sigma times T to the 4th, where E is emissivity. And this is what we know as the Stefan Boltzmanns Law. Now, this gives rise to what we discussed earlier in our QRAD equation as the application of Stefan-Boltzmanns law. What we look at most often is the relative radiation emission, which means I can have an object at, let's say, 300 Kelvin and an object at 400 Kelvin. Both objects are emitting radiation to each other. However, what we're most interested in is, well, if we're looking at radiation emission in particular, what is the net radiation emission between the two objects? And so when we look at net radiation emission, what we find is that energy sub T is equal to C epsilon sigma T S to the 4th minus T, what we call infinity to the 4th, which we can also refer to as radiation flux. Everyone following along so far? Yes, no? Don't worry, I'm about to bring some math in here in a second. So if you're getting scared, alphabet soup is coming.
If you're considering the net radiation emission, would you not need to consider like a difference in the like epsilon values for each material?
That's a good question. To an extent, yes. However, it really largely depends on the objects involved and if you expect large differences in the energy emission. And we can get more into that, but like I said, this really describes what we're looking at as flux. So remind me of this question at the end of class, and I can kind of preclude to why, one, you are correct, and two, it gets a little more complicated than that. So just hold off for about 20 minutes, and we can answer that question in a little more detail. So Stefan Boltzmanns law is really good. We get an idea. Okay, now we can consider, radiation flux that's being emitted by an object, so based solely on its temperature. Because the important thing when it comes to radiation and thermal radiation specifically, any object with an absolute temperature above 0 will emit radiation. Now, as Holly mentioned, whether it emits it well or not is related to that object's emissivity. And Stefan and Boltzmann developed this law to explain that as a function of their wonderful Stefan Boltzmanns constant. However, this law discusses the energy emission, or demonstrates total emission over all wavelengths. of radiation. So the question is, what happens if I'm only interested in certain types of radiation or certain, bands of wavelength? And so for that, we have to turn once again to our friend, old Max Planck, who in 1901 developed an expression for what we call spectral black body emissive power. And here I'll clean up my handwriting best I can. I feel so bad for all the elementary and middle school children trying to learn how to write. It's like, all right, kids, get out your iPads. And so he developed this expression for spectral black body emissive power, also known, because like I said, these scientists were getting their names on everything, as Planck's law. And Planck's law states the black body emissive power as a function of now wavelength and temperature is equal to some constant C1 divided by our radiation wavelength to the 5th power times the quantity, an exponential, of C2, a constant, over lambda T minus 1. And this gives you the spectral black body emissive power in units of watts per meter squared, because it's, like I said, an energy flux per wavelength, which are given in microns. Because that's just the standard convention of stating the wavelength of radiation. And so C1 is equal to 2 pi h C naught, where since all of these are constants, we can simply solve and say C1 is equal to 3.742 times 10 to the 8th watts microns to the 4th over meter squared. And C2 is equal to h C naught over k, which is equal to 1.439 times 10 to the 4th microns Kelvin. And K is equal to 1.38065 times 10 to the negative 23rd joules per Kelvin, which is known as Boltzmanns constant. Because he wasn't satisfied just sharing a constant with Stefan. See, this is what we really need. We need like Real Housewives kind of reality show, but of all these scientists putting their names in things. Just all these scientific divas talking trash about each other's scientific theories. I'd watch that.
Which came first, Boltzmann constant or the ideal gas constant, since they're proportional?
Oh, my instinct tells me the ideal gas constant. So now I have to Google it. This is how you activate my mental ADD.
We got Dr. UB on this question. He tried to figure it out too, and we didn't ever, I don't think, find a clear answer.
My instinct actually tells me that about the same time, because the really cool thing, and I forgot about this, We have time. Because I can always continue this next day. So have any of you guys ever had a discussion about Boltzmann's grave?
No.
Okay. I used to actually start this class with this whole thing. I think it was Boltzmann's grave. There's an equation carved into his headstone. And this is the bust of Boltzmann. And so yeah, I remember. I can't answer this question. So I gotta share this with you. This is really cool. This is the nerd in me. See, you're triggering this. Boltzmann's grave. I'll share you this image. Ludwig Boltzmann. So hopefully you guys can see my screen. Can you guys see the bust picture? And the equation right here?
Yes.
S equals K log W. And so the cool thing about this S equals K log W, right? What is S? For thermo.
Entropy.
K, I just told you. Boltzmann's constant. What is W? W is harder to remember.
Is it work? Or
Nope. It's abstract. W is the total number of microstates that exist within a system. You might have had this discussion when you talked about entropy. A microstate is if you had a really good camera and you were able to take a picture and literally trap every molecule in their position for one, frame. And you did this repeatedly until you basically were able to identify the maximum or total number of microstates that exist within that system. So if you had a box of gas molecules, the total number of microstates is the total basically conformations of those molecules that can exist in that box. And in Boltzmann graves, he quantified that value using his constant to discuss the true entropy of a system.
Are you writing? You're still sharing the picture with us.
I did write the equation. And so you asked about how it relates to the pressure of a system, right? What we find is that in order to get a better sense of the entropy of a system, we had to say, well, there's no really good way to, to tally up all of those molecules, right? To get a sense of the microstates. And so what did Boltzmann do? Well, he said, instead of talking about everything in terms of molecules, let's talk about things in terms of moles. And so if we take Boltzmann constant K and multiply it times Avogadro's number, what do we get?
The ideal gas constant.
Exactly. You get R. So when you say which one came first, technically Boltzmann's constant came first. However, one could argue they were developed at the same time because they're used to express the same idea, which is a sense of the states that exist within a system and how we can apply that when in the case of R, systems that have very large molecules at very large numbers of microstates. So I think that's a cool kind of discussion in terms of, the emergence of R, where it comes from, and how it relates to the thermodynamic principles that we discuss. So yeah. So there's my answer to that question.
Thank you.
You're welcome. Some people might find it a waste of time. I think it's kind of interesting and cool. In that, he had this strong sense of, identity associated with, the existence of entropy and the importance of the second law, that, it ended up literally inscribed upon his grave. All right, so back to Planck's law, the other diva in the room, one of many. So we developed this Planck's law that was able to allow us to identify for a particular wavelength of radiation emission at a known temperature of an object, what is the essentially spectral blackbody emissive power of the object at the temperature and basically in that wavelength. Which means if I wanted to know, the emissive power at a wavelength of 0.4 microns, I can calculate that simply by knowing the object's temperature. And so application of Planck's law leads us to a slew of implications associated with what we know about thermal radiation. The first one that we said is, like temperature, the emission of radiation is going to be a function of the wavelength emitted. The second implication that we find is that increasing the temperature of an object results in the emission okay, I should say it in this way. It results in two things. One, an increase in emission that we can state by Stefan Boltzmanns Law, right? But two, the emission of radiation at shorter wavelengths. And the third thing that we find is that exists a maximum. At a particular temperature. Or I should say for an object at a particular temperature.
Dr. Lopez, would you mind zooming out a little bit?
Of course, I know I'm writing a bunch. The problem with not wanting to move too slow, but not move too fast, but at the same time, speak as fast as I write.
Is this where we get involved with the Planck length and the Planck temperature?
Kind of, but not really.
Okay.
This is where I'm going to push it over to our slides that I prepared and show you essentially a graphical representation of Planck's law. And so what you should see here on this slide is we have the emission wavelength in microns on the x-axis and the emissive power of that wavelength on the y-axis. And we have curves associated with objects at varying temperatures. And so what we see is that as we increase the temperature of our object, the total emissive power increases. And at the same time, this curve that shows essentially the emissive power over all wavelengths, it shifts to the left, meaning increasing that energy not only increases the total power, but shifts the wavelengths of energy, or excuse me, radiation emission to smaller and smaller waves. What I think is also kind of interesting to note is if we look at the radiation of the sun, it peaks in terms of its radiation emission right at what we consider to be visible light. It gives you that existential question of, the development of our vision in tune to the sun, which is kind of cool. So one thing that we also notice is that, with this shift, we can kind of develop a slope associated with that maximum of Planck's law. And what we find if we do, we find that slope, we find what we call the slope of maximus power, or what's known as Wien's displacement law, which, shooting it back to the lecture, which I gotta say is probably one of the laziest ways to get your name on a law. Which tells us the slope of that line is equal to approximately 2,898.8 micron Kelvin. I can say he found the slope. Good job. Which means if I'm going to say, well, okay, what's the maximum, or say, what wavelength do we have a maximum of emission? I can say for that, lambda max, I just got to take 2898.8 divided by T. And that gives you your answer, of course, in microns. So one of the things that we find that's interesting is that, we have this log plot that shows lambda emission, right? E sub B lambda T as a function of temperature, right? So this is the Planck's law curve at temperature at T. What we find is if we integrate or find the area under the curve, what do we propose we might obtain? Well, what we see is that integration of Planck's law of C1 over C2, excuse me, lambda to the 5th times C2 exponential of C2 over lambda T minus 1 d lambda. So if we integrate Planck's law over all wavelengths, what we're left with is simply sigma times T to the 4th, which means integration of Planck's law over all wavelengths yields Stefan Boltzmanns law. So good news, the science works. Any questions?
I want to go back to that question Holly asked earlier about emissivities and different objects.
Oof. All right, let me try to give you the simple answer. So if we have two objects and we're interested in the radiation associated with those two objects, right? And we're wanting to know the net. And so, yes, we can consider the implications of the emissivity of both objects. And what we were left with is an effective emissivity, where we can calculate this effective emissivity. All right, let me, I'm pulling up the equation now and just double checking these notes. As 1 over the initial emissivity plus 1 over the second emissivity minus 1 to the inverse. Which makes sense. To do a check, if we had two black bodies, E1 and E2 would be 1, which means we would have 2 minus 1, or the effective emissivity is 1. So if you want to get technical, or actually it wouldn't be Ts minus T infinity, it would be T1 minus T2, because now we're interested in radiation between two particular objects. But to be honest, even looking at some of this stuff can get really complicated, particularly when we're looking at a surface area. Primarily because let's say I have a surface, right? And I'm interested in identifying the radiation that can be emitted by that surface. Oops. I have a whole lot of ways in which I can consider the implications of radiation emission by that object. What we've looked at thus far only considers what I would argue kind of like a base level view of radiation. But we stated radiation is a wave, correct? And so to understand, let's say this object's going to emit radiation, right? In which direction is it emitting that radiation?
Every direction.
Exactly. It's emitting radiation in every single direction, which means that if I'm like, once again, looking between those two objects, not only am I interested in what's the energy emission. Let's say I've got my ground, my object here is this, and then I've got a balloon right here, right? Energy emission on this balloon. Well, this surface is emitting radiation in every direction. Which means, yes, I can quantify the emissive energy by Stefan Boltzmanns Law, but I have to consider, well, what's the intensity of the energy that actually reaches that object. Because once again, if it's kind of this, semispherical object, when I really look at this in a three-dimensional sense, the intensity of this radiation that's going to actually reach that balloon is going to be a strong function of distance, right? And so I have to consider, well, what's that surface, surface element of radiation that actually results in that total travel. What that means is I have to consider these systems irregardless of the actual surface. But when I'm looking between two objects, you end up having to need spherical coordinates to truly understand the angles involved in determining the intensity of radiation or radiation intensity. Which we can quantify. I think this is I sub E theta sub V. So like I said, this is now we're going down another level in our inception exploration. Which, in order to solve for that true energy, it requires double integrals. But I'm really not going to want to have you guys do a bunch of whole double integrals. I don't think you want to do double integrals in solving systems in spherical coordinates. So we're going to just stick to looking at, Planck's law for now. You guys agree? Well, if you really want to jump into this, it's probably not the best way to end the semester, but it's fun stuff. This would be good for like a full-on or an advanced heat transfer course. We don't got to do that today. But speaking of, I think this is a good place to stop. I got a couple more things to go over, and we can work a couple examples Monday, and then we'll do some final exam review. Now, like I said, we're really not gonna do a whole lot for this in terms of what you should expect to see on the final. This is really just kind of bonus opportunities. You can use some of the information we're talking about today to solve bonus homework. I have in the past put a radiation example on the final as like a 10, 15 point bonus. So that can happen. So never hurts, right? A little help at the end. No, students usually don't complain.
Yeah, any bonus right now would be wonderful.
Yeah, I've seen some synthesis assignment grades and homework grades.
Yeah.
It happens.
What's the final?
That's a good question. I don't know, canned administrative answer would be to, please refer to the Ole Miss academic calendar, final exam schedule.
It's the Tuesday before Thanksgiving is our final.
Is it really the last day of finals?
It's
You guys
the last day.
See,
At 8 a.m., I believe.
at 8, yeah, I know it's at 8 a.m. That's true. So yeah, it will be Tuesday, November 24th at 8 in the morning. So there's to answer your question. Thank you, those of you that were able to help me answer. So you have plenty of time to study.
Oh, I'm sorry. My Zoom crashed. I didn't hear what happened in the last minute or so.
No problem. We just answered your question.